Okay, and so this is our table of contents. And just so we remember, anything that has a black diamond, what do we know about black diamonds? They are enriched and they are optional. So for example, 2.1c is enriched and it is optional. 2.1a, there's going to be some sections that are optional and they will be marked. You're not impressing me so far. If you're like, yes, we will work together, we will be quiet, we will pay attention, that's not doing it. Discovery of the nucleus is also optional. All right, the long periodic table is optional, and all the rest of it is for all of us. Some of you may have done some of this in grade 8. Some of you may have done none of this in grade 8. It doesn't matter. I teach it as though you have never seen it before. Yes? So let's start with...
Now have grades 11 and 12 and teachers down to the gym for Mountain Madness. Grade 11 and 12, please go to the gym for Mountain Madness.
We're going to be on page 5. Okay, page 5. Okay. Did everybody get a book? Everyone has a book? Okay. I need to get myself one of these also. Okay, there we are. Yes. Yeah. As long as you're quiet and you don't disturb anyone. Micah, could you get the door for us? There's just a bunch of noise in the hall. Thank you so much. All right, here we go. I'm going to put on the closed captioning. If there's anything you can't see and you'd like me to stop it and just take them off. Sometimes because these videos are quite old and the sound is not as good as it might be, sometimes it's hard to understand. So we will do this. All right, so that's the first blank you can fill in. 2,500 years. We are on page 5. Page 5. So a long time ago, they were thinking about atoms, although they didn't really know what they were talking about. So you take something, you cut it in half and cut it in half again and again and again and again. And then you can't cut it anymore. And he called those little things atomos, which sounds like atom. And that's where we got the word atom from. Okay, so you're going to fill in that box there, Dalton's model of the atom. Dalton. Okay, so I'm just going to take the subtitles off for a moment. So matter consists of, what's that word there? Indivisible. What does indivisible mean? If something is divisible, what can you do with it? You can divide it. If it is indivisible, you cannot divide it. Okay, so not dividable. What does that sound a lot like? Does that sound a lot like something that's uncuttable? Yeah? Okay. So 2,000 years later, they're still thinking the atom, or at least they've rethought that the atom is these indivisible, uncuttable particles. And then Dalton also thought that the atoms arrange in different combinations. So you want to fill in that box, combinations, to make different compounds. Okay, so this would be a compound with 1 yellow and 4 red atoms. This would be another compound with 1 yellow, a pink, and an orange atom. And there's a little note at the bottom of your page, and it says this model is called the billiard ball model. Do you guys know what a billiard ball is? It's a pool ball, essentially. But when I say pool ball, you might think like beach ball, but I mean like a pool table. Yes, you guys know, like, right? Billiard ball. So they call it the billiard ball model because the pool balls are very hard. They're not divisible, like they bounce off each other, and they actually behave a lot like we can imagine that atoms behave. Okay, so we're going to flip to page 6. All right. And this is called the plum pudding model. Okay, plum pudding. And I think it was given that name because J.J. Thomson was from England. And in England, a very famous dessert was plum pudding. And we will talk more about plum pudding very soon. This guy here, this teacher, his name is Tyler. Okay, Tyler DeWitt. And Tyler is going to explain that you don't have to think of it like plum pudding because many of you have probably never eaten. Anyone eaten plum pudding? Nope. That's what I thought. Anyone eaten a blueberry muffin? Chocolate chip muffin? Okay, so you can imagine that the plum pudding model, you can think of it, thank you so much, as a blueberry muffin model. And I'm going to let Tyler explain a little bit more about what that is. And we need a book for you. We are on page 6. There we go. You're welcome. And we're on page 6. Okay, so this is one of the things about nature. Nature loves it when the number of positives and the number of negatives are equal. Yes? So if you have 3 positives, nature likes it if you have 3 negatives, okay? Those will cancel out and give you an overall charge of 0. So it's like if you have a positive 3 and you add it to a negative 3, what do you get? 0. Okay, so that's what nature likes, is when positives equal negatives. It likes we call it a charge balance. The positives balance out the negatives. Now, I've lost my page here, so let's just make sure we've filled in everything there. Page 6. Okay, so the positive and negative balanced each other out, so the whole thing was electrically neutral. So that's at the top of page 6. Electrically neutral. Okay, that's the fill in the blank in the paragraph. And one thing you're also going to notice, Tyler has misspelled Thompson. There's no P, it's just Thompson, but it doesn't matter. I don't care how you spell it, okay? But I've corrected it in your book, so it is correct there. All right, and make sure that you've filled in the little box. We've got a little negative there. You're going to fill in the word electron in the box beside our little blueberry muffin model. And where the positive, you're going to say positively charged pudding. Okay, so if you've not filled that in, make sure you fill that in. Okay. So this is the nuclear model. And it was discovered by Ernest Rutherford. And you're going to label the nucleus. So in our little paragraph, all the positive charge of an atom was concentrated at its center. So if we're here, whoops, I've gone one page too many. All the positive charge of an atom was concentrated at its center. And besides that, atoms were pretty much what? Empty space. Now, are there any blanks or anything that anyone missed? We're good? Okay. Rutherford. So you can see he's color-coded the red to be positive. So Thomson thought the red was all spread out all throughout the atom, whereas Rutherford said, no, all the positive is in the very center. Okay, so we're going to fill in a few things. This is the Bohr model, B-O-H-R. And his name was Niels Bohr, B-O-H-R. And what did he call these little pathways around the center? He called them orbits. Okay, so he called those orbits. So we will still use the Bohr model a lot, especially in grade 9 and 10, because it is useful. Lots of models that aren't accurate are useful, all right? But we're going to discover that atoms are a lot weirder than that, okay? They're not just these little electrons traveling around the, what's the center called? The center is called the nucleus. And the electrons in Bohr's model behave like little planets going around this nucleus, which is like the sun, okay? But that's not what it really is. Okay, and I'm just going to pause there because this is a big, long name, okay? It is the quantum mechanical model. And if you can't see it that well because it's too small, I'll write it up here. That is the quantum mechanical model. And the man's name is Erwin Schrödinger. Fro, that's a lot of letters. And then ding. So Schro, and then ding, and then Now you'll notice that this model also has another name, which is kind of nice because quantum mechanical model is quite difficult, but what else is it known as? The electron cloud model. That's probably easier for you to remember. You don't need to remember both. You just need to remember one. If you know both, that's great. If you know just one of those names, that's fine. So electrons don't spin in orbits. Electrons don't spin in orbits. It's more like they are hyperactive flies. And they buzz around the atom and sketch out different shapes. Yes? Yep. If you take time-lapse photography of the hyperactive flies, you would see over time it sketches out a particular design or shape. These hyperactive sketch-out shapes are called orbitals. Okay, and now we're going to go watch the thing again. Okay, so we have another orbital, okay, and it looks like two teardrops next to each other, so we can fill that in. Some of these shapes were spheres. Others look like two teardrops next to each other. Okay, so we again have the quantum mechanical model, and it contains protons and neutrons. Who discovered protons? Ernest Rutherford. Who discovered neutrons? James Chadwick. So we have our quantum mechanical model that contains protons and neutrons. Where are the protons and neutrons in the atom? Yeah, they're in the nucleus. So the protons and neutrons are located in the nucleus, which is at the center of the atom. So we have our protons, we have our neutrons. And then what is happening with all this like squiggly woo? What's all the squiggly stuff? Yeah, those are electrons. Okay, so we have Ernest Rutherford. We have James Chadwick. Whoops, I forgot the W. Not Chadwick, Chadwick. Okay. So one of the key concepts in Science 9 that you are supposed to learn is that scientific models change over time. Yeah? And so we're actually going to look at the progression of these models and how they came up with it. Okay? How did Thomson end up with the idea that we had a positive ball of dough with little electrons stuck in there like blueberries in the blueberry muffin? How did he think of that? And we will look at that shortly. Okay, we're going to take just a break for a moment, and we're going to take a look at this page here. So Tyler talked about it a little bit, but what do you think? Why would we use the less accurate Bohr model very often in science class when it's not as accurate as the... It's easier to draw, right? Easier to draw. It shows the electrons more clearly. Yes, I can say I have 1, 2, 3, 4, 5 electrons here. How many electrons are in that wacky little cloud? Right? It's hard to tell. Easier to see the number of electrons. Now, I'm going to start using some abbreviations. What do you think E minus stands for? E minus stands for an electron. What do you think could stand for a proton? P plus. Because electrons have a negative charge, protons have a positive charge. And finally, we are going to have the neutron. Anyone want to guess the symbol for a neutron? N, yep. And we're going to put a little 0 at the top because it is neutral. Neutrons are neutral. And all together, these 3 particles are called, these are the 3 subatomic particles. Now we have a prefix here. Do you remember we learned some prefixes about graphing? Do you remember those prefixes we learned? What's the prefix that means beyond? The prefix for beyond is extra. The prefix for between what's that one? Inter. And now we're going to add one more. The prefix for anyone want to guess what sub stands for? Subatomic. Sub usually means below or under. Okay? If you go in a submarine, where are you going? Underwater. If you are at a sub-zero temperature, what's the temperature like? Below 0. So the prefix for below is sub. In this case, subatomic particles are smaller than the atom. That's what we mean by below. Okay? There are lots of other subatomic particles, but we won't worry about them. You don't need to know about muons and leptons and quarks. Anyone learn about quarks last year in Science 8? Yeah, you had a very enthusiastic teacher, because I look at it and I'm like, you don't need to know anything about quarks unless you're going into physics. Because it really is, there's a lot of physics involved in that, and physics was not my area of study, so I don't know a lot about quarks. Okay, can you think of a time when it might be useful, it might be more convenient to use the billiard ball model of the atom? First of all, if you had to draw the billiard ball model, what would that look like? Show your partner what a billiard ball model of an atom would look like. Hopefully you've drawn something that looks like that. Yes? Sure thing. Why might we use something like this? Yeah? Yeah, if we want to describe many atoms and we don't want to get too detailed in drawing them, okay? Again, it's easier to draw. It's useful for many atoms. So if I wanted to draw, say, a solid metal, I could just draw it like this. Bunch of atoms stuck together. Can you imagine if I had to draw each of those as a Bohr model? That would take so long. And what if I had to draw each of them as like little squiggly things all over the place? So long, so crazy, so messy. Yes? And let's say I wanted to draw water. Do you guys know what water looks like? A water molecule. H2O. So a water molecule, H2O, the 2 goes down at the bottom. Okay, it's a little number 2, it goes at the bottom. And that means that we have one oxygen and it's attached to a hydrogen, and it's also attached to a second hydrogen, hence the H2. We have 2 H atoms. How many O atoms do we have? 1. So if we don't put a number down at the bottom, that means we have 1 of those atoms. It does look like Mickey Mouse, absolutely. Good on you for noticing that. So this is why we might use a model like that. I could draw a Bohr model of water, but it would get a lot more complicated. Yeah. I'm going to just draw a very, very quick Bohr model of water, and you can see why I might choose not to do that. So in my nucleus, for oxygen, I have 8 protons and 8 neutrons. And then in my first shell, we call that a shell, I have 1, 2 electrons. And then I have 1, 2, 3, 4, 5, 6 electrons, and that's my oxygen. And then my hydrogen, in my nucleus, I would have 1 proton, and it has 1 electron. And then my other hydrogen, it would have 1 proton and 1 electron. Do you see how much more complicated that is? Right? And it would just take us a lot longer to draw it if we had to draw it like that every time. You don't have to draw that if you don't want to, okay? But that's what a Bohr model would look like. What did we call this model? Tell your partner. Starts with a B. What's the second word? Ball, and we have a billiard ball. Who was the scientist who goes along with the billiard ball model? Yep, it's Dalton, John Dalton. You don't need to know his first name, but you do need to know his last name. Okay? Who is the scientist who did the Bohr model? It was Bohr. Okay, Niels Bohr. You don't need to know his first name. Okay? And I think what we could do is, oh, we have that much time? Okay. We're going to take like a little stretch break. Would you like a stretch break? Yes? Okay. So we're going to stand up. Everybody stand up. Is it nice outside today or is it raining?
It's nice.
It's nice? Should we go for a little walk around the parking lot? Yeah. All right, I'll meet you guys at the bottom of the stairs.
Yeah, so hang up for a minute. So the game is my piece, and so I threw a piggy back and accidentally hit Stacey's face. It was really funny. Well, I was there that day. I didn't even bother y'all. I had a really bad reputation last year. Just that you had them on the out.
Yeah.
We all did.
Yes. So we're going to take another minute while people fill their water bottle. You can just relax for a moment. Okay? We got people filling water bottles, going to the washroom, whatever. Gentlemen, go sit. Go sit. Go sit. Go. Thank you. Okay. So now we are on page 9. Technically, this is enriched material, but it's kind of interesting and it's also very doable for a lot of you. So if you want to earn, yes, you don't have to. But you won't impress me, and it'll make a difference on your comment on your report card. What kind of comment? Chose not to take advantage of challenging material, right? And it should be like, just try and be a little interested in it. Just try and see. Maybe it'll be interesting, and maybe it won't, and maybe you'll just be like, okay, I heard it today, and I never want to hear it again. That's fair, okay? So we're going to watch a little bit of Tyler doing this experiment. And here we go. So who did this? J.J. Thompson. So you can fill in Thompson and his co-workers. What did we call that model? The tiny indivisible particles? The billiard ball model. And who came up with that? Dalton. Dalton, billiard ball. Dalton, billiard ball. Say it with me. Dalton, billiard ball. Dalton, billiard ball. Everyone. Dalton, billiard ball. 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 Okay. So you are going to label the power source, okay? And you'll notice on one end of the power source, what charge is there? Negative. And what charge is there on the other side? Positive. So the power source is probably a battery, okay? This is literally like a shiny green beam of light, okay? And it was called a cathode ray. Yes? So this is for both of them. You can label them power source and cathode ray. So this is our cathode ray. It's that green thing. And that's our power source. Same thing for both of them. So what is a cathode ray made of? Did you catch that? Anyone else catch it? Shall we go back? Let's go listen again. I'll put on the subtitles too. So what are cathode rays made of? Electrons. Cathode rays are made of electrons. Let's put that on our page somewhere. Oh, you don't want to move, do you? Oh, yeah. Okay. So the cathode ray is made of electrons. And we're going to figure out how he knew that they were electrons. We know they're electrons because Tyler just told us. But how did Thomson figure that out? How did he figure out that they were these little particles? Well, that's what we're going to find out. Oop, I don't want that. Now, let's see if you guys can figure this out before Tyler tells you. So we have our cathode ray. We have a positively charged metal plate. And we have a negatively charged metal plate. Do you guys know what positive does to negative? Positive and negative cancel out. They also do something else. So positive and negative, they cancel out. I need to make that N look like an N and the T look like a T. Sorry. They cancel out, but what else do they do? I'm not sure if you've learned this yet. You have two choices. They either repel or they attract. They attract. Now, what does positive and positive do? Positive and positive, they repel. So if you put a positive near a positive and you try to put them together, what are they going to do? Yes? But what if I put a positive near a negative? Now, what if I put a negative near a negative? Yes? They repel. Okay, so negative and negative repel. So Thompson takes a look at this and he says, I got this beam here, and when I put the positive plate above it and the negative plate below it, it bends upwards towards the positive plate. Tell your partner what you think that means about the cathode ray. What does it mean? What does it tell us about the cathode ray that it bends towards the positive and away from the negative? What information can we figure out about the cathode ray? Tell your partner what you think. If you're not chatting, you're not thinking out loud. Think out loud to your partner. Anybody got any ideas? You guys are killing me. Seriously? Okay, so what do positive and negative do? Positive and negative attract. Where do we have positive? Here. What do negative and negative do? repel. Where is our negative? At the bottom. So what can you figure out if it's moving towards the positive and away from the negative? It's attracted to the positive and it is repelled by the negative. So what does that tell you about the charge of the beam? It's negative. Okay? Because if it's negative, it's going to be attracted to the positive and repelled by the negative. So this was pretty clever of Thomson to think of doing this. And that's what these, like, I'm not a very creative person, but these creative people, they'll think, I've got this beam. I wonder what will happen if I do X, Y, or Z. So he was like, I wonder what will happen if I put a positive charge on top and a negative charge on the bottom. It could have been that nothing happened. And if nothing happened, he would know it did not have a charge, but something did happen. And that allowed him to figure out that cathode rays are negative. All right, let's go back to Tyler here. Now that's what he would have expected if the beam were negative. You don't have to understand that because magnets and electricity together are fairly complicated and you don't do that till physics 12, okay? But he's confirmed his results. All right, so we're gonna leave it there for today. What's your homework for tonight? Just to study for your test tomorrow, okay? Tomorrow is your test. It's Thursday tomorrow. Tomorrow is test day. Yes. You get to either A, keep them, B, recycle them. Up to you. Okay? Probably you'll want to keep it until tomorrow at least, just so, you know. You doing okay? Haley, time to go to your next class. You look ready for the Arctic. Who have I got today? Grade 10s. Okay. How are you feeling? Are you really? Okay. I worried because so many people have gotten sick for so long. Like I've had like grade 9s. I've had people away for more than a week. Yeah. No problem. No problem. Yeah, no, don't worry. I just want to make sure you're not coming back too early. I had one student who was here today. He came back like Friday and then he disappeared again. Like he was like literally like, I need to call my mom. And yeah, he was not recovered, tried to come back, just didn't make it. Yeah. So it's brutal, whatever's going around. Woo!
I think it's just a school. It's outside of the room.
Yeah. So I don't know. Anyway.
Well, Mr. Letters, which I really want to go to.
Oh,
It's okay.
I'm sorry. That's too bad. Well, you wouldn't have wanted to be running around yesterday anyway, so yeah. All right, so we'll see how many people we have here today because both Jonah and Baran are at cross country.
It'll be like 3 people.
So there's going to be like, who else is in here? John? Is John in this block?
Yeah.
Yeah, John and Milan.
I will be.
I think they'll be here.
I'm gonna guess 5 people show.
Yeah, that's going to be about it. And so we'll just do like the little demo.
Yeah.
And then I'll give you guys a choice as to what you want to do because I recorded my lesson with period 2.
Okay.
So we can either kind of do that or you can study for your test and just watch it on the weekend. You know what I mean? So
Yeah.
we'll decide once we have our 5.
How long is the lesson?
It's not that long. Yeah. I mean, I can string it out for longer, and I certainly did.
I didn't take attendance.
No,
What?
everyone's just gonna be like, we're here. Why would I take attendance?
I was. Someone told me that they have to take attendance, and that we all have to come.
No.
You're grade 11, right?
Yeah.
Oh, yeah.
Hi.
I'm so empty. Physics
Yeah.
doesn't like us 4.
And we have we were also supposed to have Jonah and Baran, but they're at cross country.
Oh,
So I think we might only have the 5 of you guys.
I'm just.
You're just and you're not even here. Here.
Yeah.
You're just visiting us. Maybe we'll only have 4. Sure you don't want to stay?
I want to, but I don't know.
But you have another class to go to. Okay, I get it.
What class? Yeah.
Oh, me? I'm sorry. Is it in the other gym? Or
Yeah.
outside or something? Yeah.
This is like one.
No.
Oh.
It's just,
There's like about 1.
yes,
That's
that's something else.
Last year we made Milan go down the stairs.
Okay, so I'm gonna let you guys take a look at, this is our extra sample that we did of the lab thing. So I'll let you take a look at it. This is before what we do today. So you can make your observations. We did yesterday, but we're gonna do it again today with this extra sample. We'll just get the data from yesterday so it actually matches up. Hi, Tara. You make 5. We're excited to have you here. with 5 people. Super fun. With Brian, who's like a 4.5, 5.5. So you'll want to get out your book and make some observations on that. Okay?
Brian will deal with us.
And while you wait for them to get their observations done on that, you guys can come over with me and get yourself a new workbook.
Yeah, you got to do blue.
It's blue. Okay? And
Yeah, we're supposed to all the good ones. Because there is a different one. And the pages were like actually like based off of it. Oh, there's my math. It's not as big.
No. And a lot of this stuff is just like, we're just gonna barrel through it. As soon as the mold comes, we're gonna like hit the ground running and you get our way through this. And there won't be a test on this unit, there will just be a quiz. Because you'll need all these skills for unit 7. And so I'll be like, okay, and now you're just gonna apply all those skills you learned in unit 6. So units 7 and 8 use this stuff a lot. So if you're waiting and you want to do a little studying, you can do that. Or last day we did 6.1a in class. Okay, so you're welcome to work on 6.1a, which is just the very first thing, page 1 through 9, I think. Yeah. But you cannot play on your phone because that's not allowed. Sorry. I'm trying to figure out why my knees don't work properly.
These are so similar to last year, revival stuff.
That's because I use exactly the same images. It's really hard to come up with any images. So I'm like, let's just.
And it's just the first
And mostly you've had like 2 years in math, so I forget what that looks like. You've had a second semester and now you've got a first semester, so you're like, I remember what that was. Yeah. Yeah, it's just to kind of break you easy. To remind you of what different things are. Yeah. Let me know when you're done. If I'm not possible, but you're back. Pretty much done? Okay, cool. Okay, I'm bringing this over here now. You guys can all take a look at it. I'll put it sort of central here so you can all take a look. All right, and you want your lab thing out so you can write stuff down. And while you guys are waiting for them to do that, you can go and get yourself our new workbook and the answer key just under the periodic table there. The blue one.
Is this the fourth block?
Yes.
There's
Okay,
five.
because there's two more, but they're cross country.
There's 7 people in this class, so I mean.
Well, no, because there's the grade 11s who are at
Okay.
Mount Francis.
Like,
So,
you
yeah.
need at least 5 people on
But
there.
honestly, there's only 16 people here total. Right? Like it's a teeny tiny little block. Oh, yeah. Okay, do you guys feel like you've seen it? Okay, good stuff. Now we can go over to the fume hood. What did I do with the crucible? I just picked it up and I put it down. And what did I do with it? Did I bring it over here? Oh, there it is. Okay, come on over here. Recorded after day 3. Call it day 5. We'll just call it day 5. I know it's probably day 7, but it just doesn't matter. Hello.
Can I draw on the board?
You can draw on the board, yeah, for sure, and you can erase all my stuff too.
Oh, okay.
Okay, are you guys supposed to be at Mountain Madness?
Don't worry about it.
I said I saw nothing. I heard nothing.
Thank you.
You were never here.
Everything on this board?
Yeah.
Okay.
Okay, now we're gonna consider this because before I move and do the rest of the experiment. So we started out with steel wool, and what is steel wool mostly made of? Iron, okay. And we ended up with this sort of reddish colored stuff. What is that? Rust, which is made of iron and oxygen. So where did the oxygen come from? There, okay. Now, we put something else in here along with the iron and the oxygen. What was that? The solution, and that solution was ammonium chloride. Now, what happened? We moved to the ammonium chloride. It dried up.
She's
And
off?
so what is like kind of like
Because no, she's not.
on the top? That's the
What's
ammonium
today's
chloride.
Friday?
So it's today is ammonium chloride and what's
October 3rd.
Well, I don't know what to say.
Right now.
It's ion.
You're right, it's the second.
So what format do you
Like,
test
this
it
is
on?
What, like, shape?
Can I say good luck on your test?
Structure, so that is.
Crystal lattice, okay,
Yeah,
so you can
house
see, it's not quite as obvious on this one, one of the samples from yesterday, where it really looked like there were crystals on top, but unfortunately. So you could guess. Oh, well, anyway, so what we're going to do now is we are going to do this. Now, I'm going to think that through because we are going to be drawing that empirical formula of iron oxide. Yes. What do we need in order to find an empirical formula?
Like the wrapper.
Yeah. The wrapper.
Natural.
The compounds. This looks like raisins.
Tell me poems, tell me poems.
Oh, by the math.
Find mass.
I'm gonna go like,
Uh-huh.
what involved, right?
Yeah.
He has a
The elements, okay, so you find the mass of each element. And then
He was not looking at the
so what elements are we trying to find the mass of?
And then
So we want the formula.
Sand Valley.
Say what elements of animal belt and then there's.
Why does it keep looking at mustache?
So, what about that ammonium chloride?
Sand
We don't want it, right?
Salmon.
So what we're gonna do, if they're going to.
Salmon.
And if it's going to be sublime. You guys remember what sublime means?
That's more lost.
He's going from solid.
What is
to
it?
gas. Okay, so it's gonna go from solid to gas, so you guys are gonna see a smoke coming off. It's gonna be the ammonium chloride.
Giving off middle finger.
And because this is not really, like, I mean, it's good for heat, it's very like not like. Right. Yeah, in an ideal world, we would need all of that, but I'm gonna give you the data from another class because this is a different sample than the one that's. So we're just gonna watch this for the observations and then we'll get the data from their stuff, okay? So this is going in here, so you wanna make a description of what we are using here. While you do that, I'm gonna go turn on the gas. Great.
It seems always moving out.
You're right.
Sounds not sharp.
Wait, does he have a perspective? Should we get the strands?
Everyone's like, let me.
Any administrators would like to come over so you can play really intense, like you're in my class. Okay. Okay, what am I doing? I'm trailing this thing.
In the future, that looks a lot like iron oxide. And the plastic. This was on top, or ammonium fluoride.
Okay, we have the options like
Like that?
Spence off.
Like that, exactly, so good.
We have Spence off. We have Spence and Frog. We have Snoop Spence. It just looks like I'm calling your food. Guys, you can't do this. You can't do my food. What about sing? Basic Spence dog. What's the Spence?
She's spooked up.
Spook. You're not doing this. It is beautiful. Spencer Frog.
Spence.
And you can ask about anything. Spence.
Spinning.
Could I ask the dog?
Oh, very likely, yes.
Oh my god.
Even so, she does.
Wait, she doesn't have like gold. She doesn't have like sand. Wait, that's like braces. Wait, why was I drawing braces? I'm not drawing gold teeth. Should I just fill them in?
So, I know you are a year older, but you seem like way more than a year older. Okay. So I am now going to light our.
She just doesn't get teeth.
Hold
No
the
teeth.
What if you just draw teeth and
Okay, and.
One tooth like this.
Come on down.
She's a baby.
so like you fill her milk with
Now,
teeth.
I'll
And then
use
you
the
shave
flame,
them.
so I'm gonna open up the little windows. And I'm gonna close this for nobody wants to breathe in.
Maybe not like that.
I'm also going to turn on the fan. But eventually we should see some smoke coming off of there, so let's just give it a few minutes.
Let's do your study.
The smoke coming off.
Not a dog.
And so it's a little bit of a dodgy proposition because the fume hood causes a real flow of air, which can sometimes blow out the Bunsen burner flame.
The wheel would just be with me.
And if you look at the right angle, you can see there is smoke starting to come up now. If you can't see it, feel free to get closer and kind of move around until you can see it. Madness there. Get close. It's okay. Behind glass.
Yes, it looks.
What color is the smoke? you might need to get closer and look.
I thought we were being gone. It's like, why?
Cheater. F-U-M-E. But it's to suck away the fumes. And then at some point, you'll want to take a look, like sort of like up and down on it. You know what I mean? Like so you can look inside the crucible. Maybe not just yet, but it should get exciting. Ooh, maybe soon. Maybe soon. Because at some point, usually, the smoke changes color. And you can actually see, if you look underneath, you can see that the clay triangle and the crucible itself are sort of glowing, like sort of orangey red color. So if you look underneath and up at it, you can see they're glowing, right? It's gotten so hot, which is why we're not using the glass there. Come on, almost there. Smoke's kind of like more smoke down than the day before, more exciting. All right, and if you guys just want to, I'll call you over if anything more exciting happens, if you just want to work on 6.1A. Okay, or you can be like, I choose to study my best. 6.1A will be more after Thursday. Okay. Or you can just hang out there and watch it. I would. Tyler. Ooh, and we actually can do this like a cooking show. You know, when they're like, they throw the thing in the oven, they're like, and then you take it out and it's all done because they've already made it. Well, we can do that today, actually, because I have the sample from yesterday, and you can find it. Yes. Is the smoke turning yellow at all? No? That's disappointing.
It's sort of yellow.
Sort of yellow? Okay, cool. All right. On. So what will happen is that we will wait until the smoke has finished there, and then I would turn off the gas and I would wait for it to cool. But I did that yesterday, and here's what it looked like yesterday, and I'll pass this around in just a moment, okay, so you can actually get a good look at it. But what am I going to do now? Oh. Okay, and we get the number 18.94. 18.94 grams. Which is different than yesterday. Yesterday it was 18.97. But that's what we call experimental error, right? That's why that last digit is uncertain. And this is what the final sample looked like. You guys can take a look at that one. Pass it along when you're done. You guys can take a look at this one. This one I don't think I could fit through long enough because can you see there's still some crystals in it? Right? So when these guys got their results, what two got the results? It was I don't know what it. Click on one. And make so you can make your observations of that. Good luck on test. So cute. Okay, this does not fit in here. I would put it back in this one.
Miss Franks.
Yes.
We're done.
Okay, thank you. And you got a chance to see it as well? Perfect. Thank you. Okay, so for the rest of the lab, what you're going to do is you're going to find the empirical formula of the iron oxide from the lab data. You're going to compare it to the actual formula, which is Fe2O3. Okay, maybe you'll get the same, maybe you won't, I don't know. You're going to find the ratio of oxygen to iron in each case, both the formula you got from the lab and from the actual formula. And you're going to say, is my actual ratio of oxygen to iron too big? Do I have too much oxygen? Or is it too small? Do I have not enough oxygen? Or is it just right? Is it the Goldilocks? And did we get our actual formula? If it's too much, what could have caused that? If it's too little, what could have caused that? And I do want to draw your attention to the word error. I put it in quotation marks, although it shouldn't be. I put it in quotes because error means something different in science than it does in your regular everyday life. In regular everyday life, an error is a mistake. In science, not a mistake. Error just means how far are you off of the true value, okay? And usually that can be caused by something within the experiment itself. Like say, for example, in period 2, they ended up with way too much oxygen. I think their ratio ended up being Fe3O5, I think is what they got. Okay, so you can see that this is going to be more oxygen. That's a 3-to-2. That's a, what, a 1.5 to 1 over there for Fe2O3. And over here, I think it's like about a 1.7 to 1 is what they ended up with. Something like that. At any rate, this number was too big. The oxygen to the, why do I keep writing the number 7? I want to write the number 1. Sorry. The oxygen to the iron, the oxygen to the iron. And in block 2, these guys already got to see it. you can see that you'll be able to see, I'll bring it over to you, there's some little like yellow crystals still left, which means I probably did not manage to burn away all the ammonium chloride, which means when I took the weight, I'm not only measuring the mass of the iron and the oxygen, I'm also measuring a little bit of ammonium chloride, which will make my oxygen number appear too big. And that's the kind of question that they like to ask on the AP exam. They'll be like, oh, here's where you got some data. Often it'll appear in a multiple choice and they'll be like, which of these options could have caused that? So they'd be like, oh, some of the ammonium chloride didn't burn off, right? And you'd be like, ooh, that sounds like a good one, right? Or if it was too little oxygen, maybe you heated it too long and the iron oxide itself started to decompose and come off, right? Or something like that. Anyway, here you can see there's still a little bit of that yellow crystal, and those were actually on the top of the fell off. Yeah. Right? Yeah. Yeah. Did you guys want to feel it? You sure? Yeah. Yeah. Ours looks really cool. It's a little hot right now. This was the one that we did. Now, if any of you wanted like copies of quiz number 2, I have some copies of quiz number 2, and I also have some copies of quiz number 1. My first block wanted them, so they're here. If you want them, you don't need to take them. There's no